Okay, and the last week for the course, I want to talk about plasma effects. Um, this is basically talking about what kind of waves exist in a plasma as a medium. And the general context is, if you remember so far, we always assumed that everything was happening in vacuum, right? So the radiation was happening in vacuum. The electrons were, accelerating and radiating in vacuum. We never assumed an underlying medium. And it turns out in most realistic circumstances, you do have some underlying medium. The electrons are not in perfect vacuum. And so the underlying medium has its own effect on emission and absorption of radiation. And so there's a whole theory to be developed to study the effects of the medium. And we won't have time to go into all of that, but we'll do some basic ideas in the theory. And the first one is just to figure out what kind of waves can exist in a medium, right? So you know that in vacuum, the general solution to Maxwell's equations without sources are basically plane waves, superposition of plane waves, and their dispersion relationship is just omega equal to k times c. But now the question is, okay, what kind of waves can exist in a medium? And so we can any problem we encounter, once you know what kind of waves can exist in a medium, you can try to decompose your fields in terms of those waves, right? And so we did that. So if you're if you're just in vacuum, then you're just going to use a superposition of plane waves as your solution to Maxwell's equations, right? At least the homogeneous part of the Maxwell's equations. So it's always useful to know what kind of waves a medium can support. So we've kind of done this already. Some of this will be repetition, so I think we can go a little faster. So I'm going to assume an isotropic plasma. And by isotropic, I mean there's no magnetic field, so there's no preferred direction in the plasma. It's completely isotropic. Its properties are isotropic. I'll also assume that the plasma is cold. And by cold, I mean I'm going to completely, it's as if I'm assuming the plasma has a temperature of 0. So I'm going to neglect the thermal motions of particles when I write the equation of motion. So I'm going to neglect the fact that there is actually pressure in the plasma. And so particles exert some pressure on each other as a fluid, collectively as a fluid. So I'm going to neglect all of that, and I'm just going to say it's a cold plasma. Yeah, so we can go a little faster because we have done this already as one of the problems. So these are the Maxwell's equations now written in Fourier domain. So I'm assuming that all quantities go like this, which means that, if you remember, curl becomes k cross, divergence becomes k dot, k is the wave vector, and derivative with time just becomes multiplication with omega, and so on. So these are the, you can pause and check. So these are the Maxwell's equations. And of course, we have the equation of continuity. So that's basically divergence of the current being equal to the divergence of the current plus time derivative of the charge density being 0. Okay, so that's the equation of continuity. That means the charges are not getting destroyed or created. It's similar to the fluid continuity equation, where you say the divergence of velocity is related to the time derivative of density of the fluid. Okay, so in a cold plasma, here's the equation of motion for an electron, right? So this is force equal to, this is just the Lorentz force, basically. And again, we're going to assume that there's no external magnetic field. And so any electric and magnetic fields that exist are the fields of the waves themselves, which the medium is supporting. Okay, so we're going to self-consistently solve for the electric and the magnetic fields and the motion of the plasma particles. So this E and B are basically the electric and magnetic fields of waves that exist in a plasma. And so, V is far, far less than C. So you can neglect the magnetic part of the Lorentz force. And so you get this simple equation. Again, you can write that in the Fourier domain. We've done all of this in a problem. So this must be basically be revision for most of you at least. Anyway, you put all of that together, and then you do the usual trick to get to a wave equation. You take curl of Faraday's law, and then you substitute Ampere's law from it. And when you do that, Ampere's law has a current term, right? So you'll have an equation in terms of the electric field and the current, because you got rid of the magnetic field by using Ampere's law. Um, Now the current itself, you've just solved for the current using the dynamics of the electron, right? So this is a standard procedure to figure out waves in a plasma, is to, do the same things with the Maxwell's equation, where you take curl of one Faraday's law and substitute Ampere's law. Uh, and then in the end, you need some kind of a relationship between the current and the fields, right? And so that relationship comes from the dynamics of the charges. And in this case, we've taken a very simple dynamic where, it's just the electric field applying force on the charges, and then it finally leads to a relationship between current density and electric field. This is basically Ohm's law. I mean, you've encountered this also before, where this is the conductivity term. Anyway, you put all of that in, you have a triple product vector identity to expand this here. Again, you can pause and go through the algebra here, but it's pretty straightforward. In the end, you'll get a vector equation, right? So that's the vector equation, which means that it has, you can write that as an equation in x, y, and z. Now, without loss of generality, let's assume that the k vector, the wave vector, is along the z-axis. So you get an equation for the x component of this vector equation, y component of the vector equation, z component. X and y component have symmetry because, the problem is symmetric about the z-axis, right? So x and y component, the equations look exactly the same. So what are the non-trivial solutions? By non-trivial, I mean you can always put Ex equal to Ey equal to Ez equal to 0, and then it'll satisfy the equation, but that's not what we're interested in. So the non-trivial solutions would be, one solution would be to set Ez equal to 0. That means this equation is satisfied. And now to satisfy these two equations, all you have to do is to take the coefficient of Ex and set that to 0, right? So you get this, and you get a dispersion relationship. So you get omega square equal to omega p square plus k square c square. I think we have derived this before. This is the wave dispersion relationship in a plasma. Now the other solution, of course, is to set Ex and Ey equal to 0 and set the coefficient of Ez here equal to 0. Then everything is satisfied. It's not a trivial solution. So the second solution, basically, if I set the coefficient of Ez equal to 0, I just end up getting omega equal to omega p. Okay, so the first solution has Ez, which is 0, and then Ex and Ey, which are transfers to the wave vector. So it's a transverse electromagnetic field. So this is the plasma component of the free space wave, electromagnetic wave, which you solved for. The only difference in the dispersion is this omega p square term. So there is a difference in the dispersion relationship because of that term. Now the second solution itself has Ex and Ey equal to 0 and only Ez. So you have a electric field in the direction of propagation. So it's a longitudinal wave, and it has no dispersion, right? It has omega equal to omega p. So there's no spatial dispersion, let's say. There's no dependence on k in the dispersion relationship. Actually, the k terms cancel out. So there is no spatial dispersion in this wave. And the wave always has a frequency given by the plasma frequency. Okay. One interesting thing which I'll introduce here is group velocity. So group velocity is the speed at which information propagates in a wave. You can think of this as the speed at which a band limited signal can propagate. So a signal with a finite bandwidth, right? So think of a pulse. Actually think of anything realistic, any realistic waveform like a pulse, anything that is not a pure sinusoid existing from minus infinity time to plus infinity time, right? All of these are band limited signals. So all of those propagate at the group velocity. Of course, you can, group velocity is defined by d omega by dk. You can calculate that. And because there's dispersion in the medium, the group velocity is now dependent on omega. So in free space, the group velocity is just c. It doesn't depend on omega at all. So all waves travel, all wave packets travel at the same speed. But once you have a plasma, you have dispersion. Now, at different frequencies, information is propagating at different rates, right? And so if omega far greater than omega p, you can linearize this, and we'll use this to do some problems. Turns out that this is an extremely useful phenomena to do a lot of important astrophysical measurements, is to exploit this dependence of group velocity on the frequency itself. And it turns out that you'll actually get to make very precise measurements of some interesting plasma parameters in astrophysics. So we'll do a couple of, we'll do at least a problem like that in class. Okay, so that's what isotropic plasma looks like. Now, what I want to do is, I don't want to leave it hanging here, but give you a little bit of intuition about on plasma density oscillation. So at least the longitudinal solution, the second solution, where I said omega equal to omega p. And I want to do that because you have an intuition for what the first solution is. It's a transverse electromagnetic wave, and you already know you've used that before. But I think this hasn't been really introduced to you. The fact that you can have longitudinal electric field oscillations in a plasma, I think that is new. And this wave seems to have a strange property in that it has no spatial dispersion, right? Omega is always equal to omega p. There's no k in the dispersion relationship. As it turns out, that the absence of K is a result of us making a zero temperature assumption. And I'll show you some simple algebra that proves that that is the case. Okay, so we want to get some intuition for what these waves are. And because they're longitudinal waves, they involve longitudinal displacement. So there's an electric field which is pointed in the direction of propagation of the wave. So this electric field is going to accelerate the charges, right? And so you have a wave on the electric field. So you have an electric field that is varying uh, um, in magnitude and direction. In magnitude, it can be all positive or negative. It can be pointed along the direction or opposite to the direction. But you have a wave-like variation of the electric field, which means that you also have a wave-like variation of the Lorentz force. And so you also have these charges which are responding to the electric field, and they're doing longitudinal oscillations in the plasma. So it's really like a sound wave which is going through the plasma. You have the particles in the medium moving longitudinally. If the wave is propagating this way, the particles are doing this kind of longitudinal motion. So literally like a sound wave, right? I mean, that's kind of the picture you should have in your mind. So let's take a closer look at it. Now, let's take a look at it assuming that the plasma is a fluid. Okay, we really want to understand what these longitudinal waves are, and I'm going to really treat the plasma like a fluid. So if you go back to some of the basic ideas in fluid dynamics, you basically have two important equations, the momentum equation and the continuity equation, right? I mean, I'm just taking you back to your basic hydrodynamics or fluid dynamics. So if I take an equilibrium state where the equilibrium electric field is E, equilibrium velocity is V, equilibrium density is N, okay? And then I say I'm going to make a small perturbation from that equilibrium, right? And that's how I set up a wave, right? I make a perturbation from equilibrium, and that perturbation creates disturbances that travel. So I'm going to write V as V plus delta V. I'm going to write E as E plus delta E, N as N plus delta N, right? And then I'm going to say that, dV by dt is equal to, I'll assume that the delta V is the departure from equilibrium. So in equilibrium, all of those equations are, exactly satisfied. Basically there's exact momentum balance, there's exact continuity and all of that. So what you can do is you can write the perturbed quantities, right? And again, I don't want to spend too much time on the algebra here because I really want to give you an intuition for what is happening rather than actually ask you to derive the whole thing. So I've written the perturbed quantities. The momentum equation being acceleration is given by just the Lorentz force, right? The electric part of the Lorentz force. Again, the continuity equation is just fluid continuity, right? And then I'm going to take Gauss law, okay? Because I'm not really interested in solving for E here. I'm not really solving for the electromagnetic waves. I really want to know what's happening to the density oscillations, okay? So I don't need to basically use Maxwell and Ampere's law to get rid of the magnetic field here. Like, I don't really care. I'm actually trying to get rid of the electric field itself. I want to see what happens to the density perturbations in the plasma. So I'm just going to simply use Gauss's law because it relates the electric field to the density, right? And I'm going to use that to get rid of this electric field here in these three equations and try to write a differential equation for the density itself because I want to see how the density is changing. I'm not really interested in solving for the wave equation here for the electromagnetic part of the fluid. So it's pretty easy. I mean, again, standard stuff, take the time derivative of the continuity equation, and then substitute from the other equations. It's pretty straightforward. And then you get a second order differential equation in n, in delta n, okay? And so you get a second order differential equation in time. This is a simple harmonic oscillator, like you recognize this to be the square of the oscillation frequency, right? So what this is telling you is that if you take a plasma and then you create a longitudinal perturbation in the plasma, then the electric field and the density, that perturbation is going to propagate in the form of a wave. Um, and the driving and the restoring forces in the plasma are set up such that you get a wave exactly at the plasma frequency. That's the only wave that the plasma supports, is propagation at the plasma frequency. Right, and this is, this is the equation of box on a spring, right? That's what it is. This is the square of the frequency of oscillation. Now I'm going to end this video with just a little bit of a segue into, in realistic plasmas, what I call warm plasma, where I'm not going to disregard the fact that the plasma itself has pressure, which provides part of the restoring force in the oscillations. So far, when I write the equation of the momentum equation, I've only written the Lorentz force, right? I haven't written any other forces, but in a realistic plasma, the plasma itself is a fluid, right? So it is going to exert pressure. So when I try to perturb the plasma, I'm going to inadvertently increase the pressure in the direction of the perturbation, and it's going to create a restoring force because of the pressure in the fluid itself. So including that is like including the thermodynamic effects of, I mean, basically it's like including ideal gas law into the picture, right? So let's bring the gas law into the picture by treating the plasma as a gas. So again, my intention is not to, get stuck in the algebra here, but to give you an intuition for what's happening. So again, I said this, take the same set of equations, but here's the momentum equation. I just don't have the Lorentz term here. I've just added another term. Okay, so gamma is the adiabatic index of gas, K times T. This is basically the pressure, gradient of the pressure, you can see, I think. So for instance, N is the density, right? So if I multiply the entire equation with the density, then I'm going to get, actually m times n is the mass density, right? So let's multiply the entire equation with the mass density, and then you'll recognize what this term is. So let's get rid of mn here by multiplying the entire equation with mass density. So kt times delta n is basically the gradient of pressure along the x direction. So I've just assumed a one-dimensional situation here. I'm just assuming the wave goes in the x direction. This is nothing but the gradient of pressure, right? So the gradient of the pressure is basically the term that enters the momentum equation to account for the pressure, right? So the rate of change of momentum, one of the terms is going to be the gradient of the pressure. Yeah, so again, you go through all of this, but now this extra term, if you go through the same procedure as what we did here to get rid of the electric field and write a differential equation purely in n, what ends up happening is you get spatial dispersion because of this term. So you get the same equation here. Sorry, this should be a delta n here. So you get the same kind of a Poisson equation here, like box on a spring, right? This is omega p squared. So this is the frequency of oscillation. But now you have an extra term here, which is a second order partial derivative with x, which means it's going to add spatial dispersion. So now if I write a dispersion relationship, I'm going to have a spatial quantity. How do you write a dispersion relationship? Well, just go to the Fourier domain. Just say delta n is proportional to some kind of a wave, then the non-trivial solution is going to give you the dispersion relationship, right? So here's the dispersion relationship. And so now you can see that you don't have waves exactly at omega p. You actually have spatial dispersion too. So that means that these are basically waves which travel and they have some spatial dispersion. And so these are called Langmuir waves. And Langmuir waves are just plasma density oscillations. So you have oscillations in the plasma density and the electric field. And so what's really happening is the electric field pulls the plasma, but the Coulomb force restores the plasma, right? Something like that is happening. So the electric field tries to create a charge separation between the positive and the negative parts of the plasma, but then the Coulomb force restores them. and then they go past each other, and then they create a wave. So it's exactly like box on a spring. Yeah, the only difference is here you have electromagnetic forces. Um, so this is how you put fluid dynamics and Maxwell's theory together, and work out what kind of waves can exist in a plasma. And Langmuir waves will turn out to be very important, because a lot of plasma processes are related to Langmuir waves. Just as an example, a lot of the processes in the solar corona are related to excitation of Langmuir waves, conversion of Langmuir waves to electromagnetic waves, and all of that. Again, we won't unfortunately have time to go through the theory there. I mean, that's another entire course by itself, is to do electrodynamics of plasmas. But I want you to know what a Langmuir wave is, why it arises in a plasma, and what its dispersion relationship is. So you might have, if you might have noticed here that this part here is basically the square of the sound speed, right? So the dispersion relationship for Langmuir waves is similar to that for electromagnetic waves, but instead of c square here, you have the sound speed in the plasma. Okay, so you can now see that if I now write down the group velocity and all of that, you would see that these waves are not propagating nearly as fast as electromagnetic waves. Um, Anyhow, there's a lot of theory to do here, including Landau damping and things like that, which won't we have time to go into. But I want you to know what Langmuir waves are and what kind of waves a plasma supports. And so in the next video, I'm going to relax the assumption that the plasma is isotropic, and we're going to introduce an external magnetic field and talk about the Faraday effect.